Hi guys, my name is Justin Sriwijaya, student ID 1318218. I'm a mechanical engineering student, year 2, from IDB. In this session, we'll discuss about grip phenomena that happens in heat-resistant alloys. To start, you might have heard about fatigue. It's a phenomenon that occurs to a material when it's subjected to alternating stress, which causes failure eventually over a period of time. Grip is almost like fatigue in a way, but in this case, temperature and constant load is the main cause of failure. It is defined as the time-dependent and permanent deformation of material when it's subjected to constant stress and high temperature. Grip itself most often causes the limiting factor of lifetime of a material, especially when it's exposed to high temperature. We can see this in applications such as turbine and power plant. It is also important to note that generally, the temperature needed for creep to happen is above 0.4 absolute temperature of melting point. So, what are stages of creep? To know that, we need to refer to the creep curve of strain versus time at constant load. From the graph, you see that there's three stages of creep. First is the primary creep, then secondary creep, and lastly is tertiary creep. Primary creep usually starts with the instantaneous deformation of a material, which basically is elongation of material due to applied load. Now we can observe that in primary creep region, there is a decrease in the creep rate as material experiences strain hardening. Secondary creep is also known as steady state creep due to the constant creep rate within that region. Steady state creep rate is very important data to be obtained during creep tests as it pictures the material resistance towards creep. After some time, the material will start to experience tertiary creep. This time, we could observe an acceleration on the creep rate, which eventually causes to failure. The time is commonly known as rupture lifetime. It is also an important data to be obtained during creep tests as it will tell us the lifetime of a material during static application on an extreme temperature. As you may have noticed, the key factor that causes creep is stress and temperature. From the figure shown, you can notice that the greater stress and temperature in general, material may experience a decrease in rupture lifetime, increase in steady state creep, as well as a greater creep strain. This all conclude to the more stress applied and higher temperature, your material will be more susceptible to creep failure. Please note that the temperature below 0.4 temperature of melting point, material will not experience further creep. Those are some of the formulas in order to calculate creep rate. Now let's look at the mechanism involved during creep. In general, there are four main mechanisms of creep: cross-slip, climb, diffusion, and grain boundary. Climb and cross-slip are both driven by dislocation, whereas diffusion and grain boundary are not dislocation based. In this session, we'll look further on the Coble creep, Nabarro-Herrings creep, which falls in the diffusion mechanism, and power law creep, which falls under climb mechanism. To understand what actually is Nabarro-Herrings creep or Coble creep, we must first understand how diffusion creep occur. To put it simply, high temperature increases the atomic diffusivity across grain boundaries, and this allows that grain boundaries parallel to stress, right here, parallel to stress, to become vacant as atoms move towards the grain boundary perpendicular to the stress region. This causes elongation. In Nabarro-Herrings creep, diffusion occurs via the crystal lattice region. So, in Nabarro-Herrings creep, the diffusion occurs inside this region. This is different from Coble creep, where the diffusion occurs mainly via grain boundaries. These are the formula to calculate the grip rate for the global grip. Okay, now let's look on the parallel grip. Parallel grip, on the other hand, is different from Naberhin's grip nor Koebel grip. It uses completely different mechanism. In this case, parallel grip is based on climb mechanism, which is basically dislocation-based mechanism. Dislocation differs from diffusion in such that dislocation in the propagation is the propagation of dislocations, where diffusion is the movement of vacancies. Please note that the temperature for parallel grip is usually above 0.6 temperature of melting point. And these are some of the formulas for parallel grip to calculate the grip rate. Everyone knows that doing an experiment took a very long time, and because of that, it is costly. In this case, grip testing is costly if you try to simulate the exact same condition of stress and temperature, because it will take years before you eventually get the result. This is a very inefficient method of data gathering. Because of this, Larsen-Miller parameter was used as a method of extrapolation data so that the data can be gathered in a much shorter period, but at the cost of doing the experiment in a much higher temperature. Larsen-Miller parameter is denoted by M in this formula. On the left, the figure shows us an example of logarithmic stress versus Larsen-Miller parameter for an S590 alloy. It shows us the correlation between the stress applied to the Larsen-Miller parameter. Please also note that temperature is in Kelvin. After knowing what grip and mechanism are involved, we can see how it correlates to the type of alloys that must be chosen for a certain application. In general, to increase the resistance to grip, we can choose material that has high melting point to reduce the effect of grip or even avoid grip. We also can choose a material that has high ASIC modulus, and we need to choose a material that has large grain size. Why we need to why large grain size is important is that if we choose smaller grain size, it will result to the higher chance of grain boundaries sliding, which of course increases the grip rate of a material. There are several methods to increase the grain size of material, and one of it is directional solidification. This method can be used to produce elongated grains or single crystal component. As a goal, we need to achieve single crystal as it has a greater grip resistance compared to equiaxial nor green or nor large grain. So that's all for this session. These are some of the reference that I took in order to produce this PowerPoint. Thank you. Peace.